Okay, so we're going to begin talking about limits. And limits are really the machinery that's going to make calculus go. So they're very important. But before we jump into limits, we need to talk about something from algebra that's going to come up a lot. And it's really subtle and it's a very common mistake in algebra. So suppose that I have a fraction, a times c divided by b times c. Okay, so here I can just think about a, b, and c as being real numbers. So my question is, does this equal a divided by b, or the fraction a over b? So your immediate answer is probably yes, right? Because a times c over b times c, both the numerator and the denominator are being multiplied by the same factor. And so it seems like I can just cancel c. And this really is just equal to a over b. But I claim that this is actually not always true. Okay, so why do I say this is not always true? Well, there's one number, c, for which this is not going to be a true statement. Think about what that number is. So the correct answer is when c is equal to 0. And so as long as c is not equal to 0, this will be true. So it is true. It will be true as long as c is not equal to 0. And even though it seems a little silly to consider the case when c is equal to 0, it's going to come up a lot when we look at the ideas of limits. We're going to be looking at expressions where there's going to be a common factor in the numerator and in the denominator, and we will be able to cancel that common factor as long as that common factor is not equal to 0. So this is a very important fact from algebra. So to introduce the idea of a limit, I want us to look at this function. F of x is equal to x squared minus 1 divided by x minus 1. And the first thing I want to ask is, what is the domain of this function? Well, the domain, this is actually an example of a rational function. And so the domain is going to be all real numbers, except for real numbers that make the denominator equal to 0. So we're going to have to exclude 1 from the domain. So we can write the domain like this. But what I really want to specify is that f of 1 is undefined. And the terminology here is important. Okay, so this word undefined specifies that 1 is not defined in the dictionary of the function f. So now the dictionary for the function f is its domain. So when I say, all right, what is f of 1? I have to go and look up 1 in my domain, in my dictionary, to see what the definition is. But I see that 1 is not in the definition. So f of 1 is not defined. It's undefined. Okay, so that's no problem. But look at this table of values here. So the first three values, I'm taking x, 0.9, 0.99, 0.999. So on the number line, what I'm doing, here's x is equal to 1. And so I'm starting by approaching 1, so 0.9, 0.99, 0.999. I'm getting closer to 1 from the left. And then here, 1.1, 1.01, 1.001, I'm approaching 1 from the right. That's just the x values. So here and here, I'm just approaching 1. And notice what's happening to my function values. As I am getting closer and closer to 1 in this direction, I'm getting closer and closer to 2 in my output. And then as I get closer and closer in this direction from the right, it also seems like I'm getting closer and closer to 2 in my output. And so it almost seems like f of 1, if I put 1 here, it seems like it should be 2. But f of 1 is undefined. I can't plug in 1 into this function. So when I have this situation where I can look at a table of values, or later I will actually look at the graph of the function, and it looks like from the left and from the right, whatever x value I'm approaching, if f of x, so the y values, the function values, seem to be approaching some number, then what I can write is this. So now I'm not saying that f of 1 is equal to 2. I'm saying that the limit is x approaches 1 of f of x is equal to 2. So in other words, if x is really, really close to 1, f of x is going to be really, really close to 2. So this is read the limit as x approaches 1 of f of x equals 2. So the limit of this function as x approaches 1 equals 2. And again, this is what you should think about. Now let me show you a picture of what's going on. So here's a graph of this function, f of x equals x squared minus 1 divided by x minus 1. And so we've already said that the limit is x approaches 1 of f of x is equal to 2. And we concluded that by just looking at a table of values. Okay, but remember that f of 1 is undefined. So something kind of weird is going on here. And if we look at actually the graph of this function, x squared minus 1 over x minus 1, what's really going on is there is a hole at x equals 1. But other than that, it really does look like a straight line. So it's just a regular function. It's actually just a line, but there's a hole at x equals 1. And notice the y coordinate of that hole is 2, which is what the limit is. So let's see algebraically why that's true. And this is where we're going to use that key idea from algebra that we introduced at the beginning of this lecture. So look at the function f of x. It's x squared minus 1 divided by x minus 1. But notice that the top, the numerator, is actually a difference of squares. So we can factor it as x minus 1 times x plus 1 divided by x minus 1. Now look, the numerator and the denominator have a common factor of x minus 1. Now, in general, this is not equal to, well, if I cancel, so x plus 1. So I can't just say, oh, I have a factor of x minus 1 on the numerator and the denominator, let me cancel them. Remember, I can only cancel these two factors if I'm assured that the factor is not equal to 0. And the factor is equal to 0 exactly when x is equal to 1. So what I can do is I can actually express this as a piecewise function. So as long as x is not equal to 1, it's valid to cancel the factors of x minus 1. So f of x really is just equal to x plus 1 as long as x is not equal to 1. Okay? And then f of x is undefined if x equals 1. So notice here that we're just specifying our function is really just x plus 1, except when x is equal to 1. It's just undefined. There's just a hole. If I go and look in the dictionary for x equals 1, there's just a page missing. I don't know what it is. And this is really subtle because you may say, well, what's the big deal? Why don't I just fill in this hole and just say that f of x is equal to x plus 1? Well, that's all well and fine, but that's not what f of x is. F of x, the definition, is actually x squared minus 1 over x minus 1. It's not just x plus 1. And it's going to be important to start to realize that there is a big difference between x squared minus 1 over x minus 1 and x plus 1, even though they somehow simplify to be the same thing. But the simplification really does require that x not be equal to 1. Okay, so let's look at limits a little bit from a graphical perspective. So what I'm going to do is just draw kind of an arbitrary function that's going to serve to illustrate some points about limits. So let's say we have a few different points. X equals A, x equals B, x equals C. Let's think about what our function is going to look like. Okay, so we have something like this. And then I'm going to put a hole in the graph right here. And then I'm going to go over here, draw another hole, and kind of do something weird over here. And then keep going. Okay. So this is a perfectly valid function. Now I can't write down what it is algebraically because it's just kind of arbitrary, but it's just the graph of a function. So let's look at a couple of things. So at x equals a, if I look at the graph of the function, well, f is defined at a. So f of a is defined. And then also, if I look at the function just to the left of a and just to the right of a, we see that they're actually both approaching f of a. They're both approaching the same thing. So actually, I can say that the limit as x approaches a of f of x exists. And now, again, I really need to separate what's happening at x equals a, that's just f of a, that's right here, and what's happening immediately to the left and immediately to the right of at x equals a. And so for the limit, I really don't care what happens at x equals a. I don't care whether or not f of a is defined or not. I only care whether what's happening just to the left is the same as what's happening just to the right. And in that case, the limit is said to exist. Okay, so what about at x equals b? Well, here, f of b is undefined. There's a hole. If I go and look up x equals b in the dictionary of my function, there's a page missing. There's a hole. F of b is undefined. But if I look at the limit, if I just ignore x equals b and look just to the left and just to the right, I see that just to the left and just to the right, the function is approaching the same thing. So the limit does exist. So the limit is x approaches b exists. That's like in the case we saw before with x squared minus 1 divided by x minus 1. So what about at x equals c? Well, notice that if I look and try to find a function value at c, there are two holes. So f of c is undefined. But there's actually a bigger problem than f of c just not being undefined. If I try to find the limit, so if I look to the left my function values are way up here. But to the right, my function values are way down here. So somehow the values of x to the left of c are giving me function values that are different than x values just to the right of c. So in this case, the limit is x approaches c of f of x does not exist. So again, there's two different ways of thinking. Is the function defined at a point? And does the limit of a function as x approaches that x value exist? Okay, so let's look at two very special types of functions. Let's look at a constant function . So recall that a constant function is just f of x equals c. And for both of these examples, a and c will just be any real number. So it's just kind of a representative example. So we have a constant function, f of x is equal to c. And then we have what's called the identity function. And the identity function, well, it's called the identity function because it just takes whatever the input is and it gives the same input as the output. So it just identifies what the input is as the output. And that's just f of x is equal to x. Okay, so let's think about the limits of these two functions. So the limit is x approaches a, and here a again is just any real number, of f of x is equal to what? Well, let's just think about what a constant function looks like. So a constant function just looks like a horizontal line. And specifically, it's a horizontal line passing through y equals c. So if here's x equals a, so for the limit, I'm supposed to look just to the left of x equals a and just to the right. Well, this function is always just equal to c. So no matter where I look for this function, the function values are just going to be c. So I can conclude that the limit as x approaches a for any real number a of this function is really just c. There's really not a lot of content in what I'm telling you. But if you have a constant function, and I take a limit as x approaches whatever, some real number, that limit is just c. But how about the identity function? Again, I just want to let x approach a, where a is any real number of f of x. So again, let's look at the graph of the identity function. It's just a line with a slope of 1 passing through the origin. Okay, and let's say that this is x equals a. Well, if I look, of course, f of a is just a. Here's a right here. And if I look just to the left, my function values are getting closer and closer to a. And if I look just to the right, my function values are getting closer and closer to a. So I can conclude that the limit as x approaches a of f of x, when f of x is just the identity function x, is equal to a. Okay, so hopefully you can believe those two statements. And these two statements are examples of what's called limit laws. And limit laws basically just tell you how to take limits quickly and efficiently. It's a little vague to say, oh, well, just to take a limit, just look at what's happening a little bit to the left and a little bit to the right. It's not always easy to do that for certain functions. So it's going to be helpful to have these limit laws that we can use to actually evaluate limits. And in the next slide, we're going to see a long list of limit laws. So as advertised, here's a long list of limit laws. Limit laws. And this is not an exhaustive list. And in fact, you'll notice that we still haven't talked about trigonometric functions, exponential functions, and that's all coming. But for now, we just want to get our hands on at least what's called algebraic functions. And that's basically what the limit laws are describing. So I suggest that you take a minute and look through these and just kind of get a sense of what they're saying. And what they're really saying is they're looking at the ways to combine functions and saying that if I know what the limit of one function is, and I combine it in some way with another function that I know what the limit is, so I add, multiply, divide, multiply by a scalar, take a power, or take a root, then basically the limit ends up being exactly what I think it is. Okay, so here add, I just add the limits. I multiply the function, I multiply the limit. I divide the function, I divide the limits. I take a power of the function, I just take a power of the limit, root of the function, root of the limit. So there's kind of a takeaway from this. The takeaway is not to beat your head and just stare at this for hours and hours and hours until it makes sense, because it looks a little crazy. The adage is this: to evaluate a limit, plug in the x value, so the x value that you're trying to take the limit of, so in this case we're saying as x approaches a, and see if you get a real number. Okay, so most of the time, so this is a big hypothetical, but it really is true. 9 times out of 10, when you're going through calculus, if you can just plug in whatever the x value you're approaching into the function and get a real number, most of the time, this gives the limit. And we're going to actually see why this is the case later, that for functions that are called continuous, this is exactly what it means to be continuous. If you can evaluate the function at a for a continuous function, then the function value has to equal the limit. Okay, and most functions are continuous is the takeaway. But we'll talk about that a little bit later. But for now, just know that the limit laws are telling you that to evaluate a limit, just plug in the x value that you're approaching into the function. If you get a real number, that's probably the limit. Okay. Now, the interesting thing that's going to happen, because up till now you may be saying, well, what is the point of even defining these limits if all I'm really doing is just plugging in values into functions? The interesting thing happens is when I try to evaluate the limit by plugging in an x value, and I don't get a real number. And that's what we're going to talk about next. Let's go back to the example we were looking at before. F of x is equal to x squared minus 1 divided by x minus 1. So I said that the limit laws basically said that if I wanted to take a limit, I just plug in the x value that I'm supposed to be approaching into the function. If I get a real number, that's usually the limit. So let's see an example. Let's take the limit as x approaches 2 of this function. So basically what the limit laws tell me is that I should just try to plug in 2 into this function. So that's going to be 2 squared minus 1 divided by 2 minus 1. So that's just 4 minus 1, which is 3, divided by 2 minus 1, which is 1. So supposedly, the limit is 3. And indeed, the limit is equal to 3. And that's the beauty of the limit laws. If I try to take the limit of a function, I should just try to plug in the x value that I'm approaching. And if I get a real number, like I said, 9 times out of 10, maybe even more than 9 times out of 10, that's going to be the limit. Okay. So like I said before, the problem comes in when I don't get a real number. So let's look back algebraically at the limit is x approaches 1 of this function. So if I try to plug in 1, I get 1 squared minus 1 over 1 minus 1, which is 0 divided by 0. So here's the million-dollar question. What is 0 divided by 0? So if you said 1, that's a good guess, but that's incorrect. This is not a real number. 0 divided by 0 does not make sense. Okay? It just doesn't. Well, just think about it this way. You're dividing by 0. Or if you want, you can think I'm taking 0 things and breaking them up into 0 groups. Doesn't make any sense. Okay? This is an example of what's called an indeterminate form. And we are going to see lots of examples of indeterminate forms later in the class. But for now, the one that you should remember is 0 divided by 0. That's an indeterminate form. It's not a real number. Okay? So my limit laws break down. I have a problem. I try to plug in 1 to get the limit. I don't get a real number. Okay? But we've already seen that the limit should be 2. So how do I get 2? Well, this is where algebra comes in. So if I look, this limit, I can start rewriting the function. So I can factor the numerator, still dividing by x minus 1. But here's the key thing about limits. Because I don't actually care about x equaling 1, I only care about what's happening immediately to the left and to the right of x equals 1. I can assume that x doesn't equal 1, so that x minus 1 doesn't equal 0. And think back to the first thing we talked about. Because I'm assuming that x minus 1 is not equal to 0, I really can cancel. So basically this limit notation, and it's very important to remember to keep this notation while you're taking the limit, because it gives me a free pass to be able to cancel the x minus 1s. And so really, I'm taking the limit as x approaches 1 of x plus 1. But now I can go back to my limit laws. Now I can just plug in x equals 1. And what do I get? I get 1 plus 1. But that's 2. And that's exactly what I'm supposed to get. So you see that we can actually solve limits in two ways. If we can look at the function graphically, we can look at limits that way. But we can also solve limits algebraically. And you see that when you're taking limits, you can actually break certain algebra rules that you normally can't break, because I'm only considering values of x near the point I'm approaching, not actually equal to the point I'm approaching. Okay, so here we have the graph of a function. And we're going to sort of highlight here the difference between function values and limits of functions. Sometimes they're the same, sometimes they're different, sometimes function values are undefined, sometimes limits don't exist. So let's see what we have here. F of 1, starting with A. So I look at x equals 1, and I go and look at the graph of my function. So what is f of 1? And here notice we're going to start using some convention that an open dot means we're not including that value, and a closed dot means we are including that value. So if I want to know the value of the function when x is equal to 1, I want to look for the filled in dot. So here f of 1 is equal to 0, because that's the y-coordinate here. F of 2, if I try to find f of 2, well, there's a hole. And I don't see a filled in hole anywhere else, so there's no definition for 2. So f of 2 is undefined. F of 3, again, I don't want to look up here because there's an open circle. I want to look down here. So f of 3 is equal to 1. All right, now let's look at the limits. The limit is x approaches 1. So I look to the left. It looks like the function is x approaches 1 from the left. The function values are approaching 1. Now, even though f of 1 is not equal to 1, from the left, I'm getting closer and closer and closer to 1. So the limit as x approaches 1, looking from the left, is 1. But if I look from the right, the function values are actually getting closer and closer to 0. So because as x approaches 1 immediately to the left, those function values are different than the function values as x approaches 1 immediately to the right, this limit does not exist. Now what about as x approaches 2? I look from the left, function values are approaching 1, and I look from the right. The function values are also approaching 1. And it's okay that the function is not defined at x equals 2. There's a hole, but to the left and the right, I'm getting closer and closer to 1. So the limit is equal to 1, and the limit exists. So as x approaches 3, we have something similar. So if I look from the left, I'm approaching 2, and if I look from the right, my function values are approaching 2, even though the function the function evaluated at 3 does not equal 2, it equals 1. But the limit is 2, because that's where the function values are immediately to the left and immediately to the right of x equals 3. And so you see we have a situation where the function's defined and the limit doesn't exist. The function's undefined, but the limit does exist. And then we have a case where the function is defined and the limit does exist. Okay, so let's try to evaluate some limits algebraically. And the nice thing here is we're going to be able to use the limit laws. So in the first one, I'm taking the limit of this function as x approaches 1. The first thing I should always do is just try to plug in, well, whatever I'm taking the limit as x approaches, so in this case 1, into the function. And let's see if we get a real number. So this is going to be negative 1 squared plus 4 times 1 minus 2. Okay, so be careful here. I'm squaring the 1, so this is 1, and it's negative, so it's negative 1 plus 4 minus 2. Okay, but this is just equal to 1, and that's a real number. So I'm going to assume that that's the limit, and indeed it is. That is the limit of this function as x approaches 1. So really the limit laws make these problems really easy. It's just evaluating the function as long as I get a real number. So now the limit as x approaches 5. Let's just try plugging in 5. So this is going to be 5 cubed minus 125. But what is 5 cubed? 5 cubed is 125. So this is just square root of 0, which is 0. And that's a real number. So that's what the limit equals. And then finally, let's plug in negative 2. Negative 2 plus 1 divided by 2. Negative 2 plus 1 is negative 1, so negative 1 divided by 2, or negative 1/2. And that's the limit. So again, the limit laws make these problems really easy in the case that we can plug in what x is approaching and get a real number. All right, so we did so great on the last example. Let's keep going. Let's find the following limits. So let's just try to use the limit laws and plug in negative 1. So I get negative 1 squared plus 2 times negative 1 plus 1 divided by negative 1 cubed plus 1. So this is 1 minus 2 plus 1, so 0, divided by negative 1 cubed is negative 1, plus 1 is 0, 0 over 0. So we are not so lucky. And you knew all good things had to come to an end eventually. We get an indeterminate form. And this is the interesting thing that happens when we go to evaluate limits. We hope that we just plug in and get a real number. But sometimes it's the case that we get an indeterminate form. But it's still important to try to plug in and see explicitly, okay, I have an indeterminate form. And now there's another way to think about indeterminate form, and that's that the limit is not able to be determined in the function's current form. So when you get an indeterminate form, it's really a red flag that means do more work. So what do I mean by that? What I mean is that we need to do some factoring or some other algebraic manipulation of the function to see what the limit is. And in this case, let's try to factor the numerator and the denominator. Now the numerator is not so hard. And notice that as I'm doing this problem, I'm going to write the limit as x approaches -1 over and over again until I actually evaluate the limit. So the numerator factors as x plus 1 times x plus 1. Okay? What about the denominator? Now this is really tricky. This is kind of, a big curveball of a problem if you haven't seen something like this before. But notice that x cubed plus 1 is actually a difference of cubes. Okay, so x cubed is definitely a cube. But this is plus 1. How is this a difference of cubes? How am I subtracting something cubed? Well, I'm subtracting -1 cubed. So notice that this really is x cubed minus -1, or x cubed plus 1. So this will actually factor as x minus -1, so x plus 1, and then times x squared minus x plus 1. So the denominator becomes x plus 1 times x squared minus x plus 1. Now normally I would not be able to cancel this common factor of x plus 1 in the numerator and in the denominator. But because I'm taking the limit as x approaches -1, I can actually assume that x is not equal to -1, so that x plus 1 is not equal to 0. So I can really cancel those factors. And so this limit is the same thing as taking the limit as x approaches -1 of the function x plus 1 over x squared minus x plus 1. Now let's just try to plug in -1. Well, I plug in -1 and I get -1 plus 1 divided by -1 squared minus -1 plus 1. But -1 plus 1 is equal to 0, and then the denominator becomes 3. But this is just 0. So the limit of this function as x approaches -1 is 0. Okay, so let's jump in and take this limit. So we're going to start by trying to just use the limit laws and plug in x equals 2. So that's going to be 2 plus 2 minus 2 over 2 minus 2. And maybe you're not surprised that this is 0 divided by 0. We get an indeterminate form. And recall what that means. It's not able to be determined in its current form. So do more work. So here, this is a little bit tricky, because it's not really clear that this factors in some way or really simplifies. So what do we do? Well, here's a note. When you see a square root, that's a red flag. To multiply by the conjugate. So we actually have seen this before in the previous lecture. So we see a square root, that's a red flag to multiply by the conjugate. So what is the conjugate here? Well, this is square root of 2 plus x minus 2. So the conjugate is going to be square root of 2 plus x plus 2. And we got to do the same thing to the top and the bottom. And it's probably worth noting that this conjugate factor is always strictly greater than 2. Well, greater than or equal to 2. And so I'm not multiplying by 0. And so what does this do for me? Well, I'm still taking the limit as x approaches 2, but notice how the function that I'm taking the limit of changes. The top becomes a difference of squares, so it's really 2 plus x, so square root of 2 plus x squared, minus 2 squared, which is 4. Okay. And then we have x minus 2 times, well, the same conjugate factor. Okay, so what actually happens to the numerator here? Well, let's see. 2 minus 4 is going to be negative 2, and then plus x. Or in other words, just x minus 2. And that's what we hope to happen. When we take these limits and we get an indeterminate form, we hope that we can simplify the function so that a factor cancels. And the factor that cancels should be the 0 divided by 0. And again, because we're taking the limit as x approaches 2, we can assume that x is not equal to 2, so that x minus 2 is not 0. So we really can cancel. Note that we're just left with 1 in the numerator. So this is the limit as x approaches 2 of 1 divided by square root of x plus 2 plus 2. All right, but now we can just plug in 2, and we get 1 over 4. So that's the limit of this function as x approaches 2. So one more example of a limit. And by now, hopefully you know the drill. The first step is always to just use the limit laws and hope for a miracle. Well, maybe not a miracle. Hope that you get a real number, and then you're done. So let's see what happens when we plug in 1. We get 1 over 1 plus 1 minus 1/2 divided by 1 minus 1. And as we feared, we get 0 over 0, which is an indeterminate form. So, like we've said before, this limit is not able to be determined in its current form. So we need to do more work. And so here, this is a mess, first of all. We have fractions within fractions, and that's always a bad day. So the first thing I would do is just try to write this as a single fraction. Now the denominator is fine, but let's try to write the numerator as a single fraction. So let's actually do this subtraction. So we're going to get a common denominator. So we'll have 1 over, so we'll have 2 over 2 times x plus 1 minus x plus 1 over 2 times x plus 1. So notice that I just multiplied this fraction by 2 over 2 and this fraction by x plus 1 over x plus 1. And then over x minus 1. So I haven't done anything, but now I can combine these two fractions. And what do I get? Well, I have 2 minus x and 2 minus 1, so that should be 1 minus x. But 1 minus x is the same thing as negative x minus 1. Okay, and you'll see why I'm doing this in a second. So notice that if I just distribute the negative back in, I get negative x minus negative 1, so negative x plus 1, or 1 minus x. So in other words, this numerator within the numerator becomes minus x minus 1 divided by 2 times x plus 1, all divided by, so that's just the numerator, 1 over x plus 1 minus 1/2, all over x minus 1. And this is where things get really tricky. And you really have to go back and think about algebra. So you have fractions within fractions. This is really like fraction division. The way I like to think about this is that in the numerator I have a fraction, and in the denominator I have a different fraction, x minus 1 divided by 1. You can always just think about a term as a fraction over 1. And so I'm dividing fractions, so that's the same thing as multiplying by the reciprocal. So this is the same thing as the limit as x approaches 1 of minus x minus 1 over 2 times x plus 1 times 1 over x minus 1. Okay, that's just the reciprocal of this term. But same old story. We're taking the limit as x approaches 1, so we can assume that x minus 1 is not equal to 0. And you see now why I wrote 1 minus x as minus x minus 1, because these x minus 1's are going to cancel. And what are we left with? Hopefully something that we can just take the limit of by plugging in. Well, we still have this negative. The numerator is now just 1, so negative 1, over 2 times x plus 1. But if I plug in 1 here, I have negative 1 over 2 times 2, or in other words, negative 1/4. So the limit of this function as x approaches 1 is negative 1/4. Once again, I'll say, hardest part of all of this is algebra.